Test 12, finally. We could put an exclamation there, right? Oh, it's not even up. Airplay's still not working. Hold on, guys. All right. So, chapter 10, 21.1, 21.2. Theory. Chapter 10 begins with the concept of temperature. It's all about heat. It's all about changing phase, but due to added heat. So our key here is temperature and heat. We talked about modes of heat transfer. So let's start first with temperature. Temperature simply measures the kinetic energy of each particle, the average kinetic energy. So something that's really hot means particles are moving rapidly. Something that's really cold means they're not moving very rapidly. We gave the example in class about the fact that if you light a match, though, even though it feels hot, it's got less energy than an ice sculpture would. Because even though the ice sculpture is very cold, there's a lot more mass to it than a simple match being lit and consumed. You can even think about this with like a small iron ball bearing being really hot, and then a cool basin of water. If you drop the ball bearing in the water, we know from calorimetry, one of our math problems, that the energy from the ball bearing that's hot will go into the water. So the water must be able to take that energy, right? So the water itself has more thermal energy in general than the actual ball bearing does, even though it's colder because there's a lot more water itself. But temperature, we want to know, is the average kinetic energy of the particles. We went on to talk about several things next. Thermal equilibrium. We talked after that about just generally heat. What's thermal equilibrium? What's thermal equilibrium? So two anything, not just liquids. Two anything go together at identical temperatures. Are you in a state of thermal equilibrium with the room? No. What's your body temperature around? On the surface, you said. On the surface? 80, 90, right? Something like that. We did it in class. The room, though, is around 70 right now. So you're non-thermal equilibrium with the room. You shouldn't be. You're not ever going to be. If you are, there's something wrong. Like you have a cold or a fever. Not a fever, the opposite. So thermal equilibrium, similar to force equilibrium, where forces are balanced, temperature is balanced. You reach thermal equilibrium always, eventually, with objects. Now, as humans, because we are generating energy and we give off heat and we are an exothermic body, it's not possible necessarily for us to get to the same temperature in the room if the room is far below body temperature. Okay, now, if we had this air conditioner pumping all day, you guys came in here and said for 10 minutes, and I walked around the room with that little temperature gun, and I measured your skin temperature, it'll probably be like low 80s, not like mid 80s or maybe some of you like 90s. It'll probably be low 80s, if not 70s, because eventually your body does cool down. When you sleep at night, the same thing happens. Your body cools down. Heat. What is heat defined as, or what is heat? Very good. They don't move. They don't move together. When two objects are at a different temperature, which causes energy to flow, creating heat. If the two objects are different temperature, though, they're not moving. So when T1 doesn't equal T2, flow of energy goes from one body to the other. That's what heat is. Okay, so when you say like you're heating something up, what are you giving it? Energy. When you say you're heating something up, you're giving it energy, literally. The microwave is a little different. It's a whole other ballgame. But you're bringing out energy from those internal structures in the molecules. You bring out water. Actually, motion comes out heated up. So heat is, again, when the two temperatures are different and there's some sort of a transfer as a result. Which way does heat transfer? From where to where? Hot to cold. Got to know that. Hot to cold always. It's never the other way around. Heat can only warm something up. When you remove heat, it cools down. But you can't add cold. It doesn't exist, right? You can't add cold to something. It doesn't make sense. You're adding energy or you're removing energy. Either one of the two. 3 modes of heat transfer. What are they? 3 modes. Okay, conduction I heard. What else? Convection. What else? Radiation. Conduction involves contact. You need to have contact for conduction to be apparent here. It's got to have contact. Now, conduction assumes the material is conductive. It's a thermal conductor. What is an example of a thermal insulator? What's a thermal insulator? What material would you use for insulation? Rubber would be good. Rubber does not transmit heat very easily. Asbestos, we would not use it anymore, but very good example, yep. Foam, Usually also gas. Remember I talked about double pane windows with air in between? Gas slows down heat transfer. It's trapped.
What are they using walls now?
What?
Like walls now? It's like that paint stuff. What's it called?
It's a new form of what used to be asbestos. Asbestos was this insulation that was used to insulate walls with a very low K value, so heat wouldn't transfer through it. I don't actually know what it is. I know for moisture they use what's called a vapor barrier, and it's like a sealant, but it's not for heat transfer. I don't know what the material is. Probably Google it, see what it is. Convection. Instead of conduction where there's contact between two materials, convection there's contact specifically between a material and a fluid. Very good, Mike. A fluid. Convection occurs when you have fluid flow over a surface. So you can think of it as contact. Because right now, isn't the air in contact with your body? So although it's not like the air is physically touching you, it kind of is. The air is flowing over your body as it cools off the room. Convective currents occur. We talk about convective currents. The air comes in the room. What happens to the cold air? Falls down. What happens to the hot air? Rises up. Hot air gets sucked out the room. It pulls in hot air, but it cools it on the way in. In the air conditioner, you have a refrigerant. I talked about Freon. It literally cools air by absorbing the energy. Hot air is being pumped into the room right now. But because this is an air conditioner, it cools it on the way in. It super cools it in a sense, really quick, right? The air that's blowing into the room, it cools off. It's not just like there's cold air outside being pulled in. It's hot air that's being cooled by the air conditioner. There's a refrigerant inside of it that takes on, it's a fluid, it flows through these different pipes. It takes on the heat, and it says, you know what, I'm going to absorb the heat. And that fluid changes phase, it's heat transfer again, turns to a gas. It then gets condensed in a condenser, using a compressor. It condenses it back to a liquid, which comes back through and it continues the cycle. But the air conditioner has to be plugged in for the condenser to work. So as you cool down the air, you're using energy from the wall to cool it down. That's what you're physically doing with an air conditioner. But it involves convective flow. Other examples of convection, you blow on food when it's hot. You heat up a pot of water. You're trying to boil for macaroni or some pasta or something you're using, right? Heat up the water. The flame touches the bottom. The hot water, what does it do? Rises to the top. The cold water comes to the bottom. So when you see boiling occurring, you're seeing higher temperature bubbles coming to the surface because that gas is less dense, and you're seeing a boiling and a bubbling at the top. Okay? Radiation involves, what is the one thing it involves? An object giving off heat. How does the energy, heat get carried to you? In the form of a wave. Very good. So it's energy from an object giving off. It's radiating heat. There's no contact involved with radiation. There is no contact involved with radiation. It acts at a distance, which is what allows the sun to warm up the earth via radiation. The energy is carried to the earth in packets called photons, and those packets are carried on a wave. It's is it transverse? I think it's longitude. I forget with photons which kind of wave it is. It's an EM wave, so it's probably both actually. That's the theory for the most part. How about thermal expansion? Can somebody comment on thermal expansion? What is it? How is it used? What's an application of it? Come on, this is straight chemistry. Oh, airplay's not working. Hold on. Keep talking though. Keep talking. What is thermal? I wrote thermal expansion at the top. What is thermal expansion? What is thermal expansion? Come on, guys. Use the key of the words. Trevor's not the only one that knows this. And Marilyn, who always answers also. Come on. Thermal and expansion. The two words together mean something is doing what? Nico, go ahead. So it expands, it becomes larger. When you heat something up, you're increasing the kinetic energy. Guys, air plays out. Right now I have thermal expansion right at the top. When you increase the amount of energy, because the particles will move faster, which expands the object. There are very few substances that are not following this general rule. But the general rule is as temperature increases, volume increases. Go ahead. Who's going to say it?
I was just going to say water is involved.
Very good.
What?
Yeah, very good. Hydrogen bond expands upon becoming a colder substance. When you go from a liquid to ice with water, it does not follow this rule. And this is the general rule. As temperature goes up, volume goes up. Volume, that's a V with a capital V. What? Yeah. Yeah, that's what I was going to say. What's the application? I went over a couple in class. I want to remember an example of this. What did I talk about in class? Talk about tires. Talk about bridges. Talk about doors. Can somebody explain any of those? Tires, bridges, doors. How do they use thermal expansion? How do they see something?
Doors in the summertime get bigger.
Yeah, wooden doors specifically. Wood swells from heat and from humidity. Those two things. So in the summertime, the door will literally stick. It'll stick when you go to close it. You go to open it, it's like pops open. Yeah. Was that one of the examples in the notes? I think that's one of the problem set questions, actually. If you've ever tried to open a jar of sauce and it's been vacuum sealed, you can't do it. What do you run under? Because metal expands much faster than glass. So the metal lid gets bigger, which makes it looser. It's amazing, actually, think about it. It's all thermal expansion. You run it, my mom showed me this when I was a kid, and I had no idea how it worked. Because we jar our own sauce. We have our own tomato sauce every year. So yeah, we vacuum seal them at the end of the year. So we have like 300 jars of sauce every year, and amongst all of our families, we just split it with the Italian families. And at the end of the year, or when we're using it, she always runs it under hot water, because when we originally, this is really cool, when you originally put the sauce in, you put the top on, it's this little plate, and then you screw on the ball jar top. It actually vacuum seals on its own because the sauce cools down, which creates a bit of a vacuum. It concentrates a little bit more. It sucks in the pressure. You know, from pressure, PV equals nRT. So if you think about this, as the temperature decreases, it causes the molecules to get closer, which creates more pressure internally. So it lowers the pressure inside, which creates like a vacuum effect. So you run it underwater, it expands the metal ring on the top, and you're easily able to open the top. A bridge works the same way. The locking mechanism in a bridge allows for the bridge to expand and contract. Ooh, okay. Frog in my throat. Damn. Ever had this? You good? Frog in your throat? Okay. Theory of, so the math involved here, I'm telling you now, 10.3, 10.4 is where the math is coming from this entire test. Okay? There was example number 1, that was calorimetry. There was example number 3, that was heating curve, where you keep adding heat to cause phase changes. There were also examples in your homework, numbers 55 and 56. I think you asked about this question in class. Okay, there were examples there. So those need to be the practice problems. I'm not going to get into it. I'm going to get into the theory now of magnetism. If you want to practice those two problems, I did extensive work with the other class. So over the weekend, look at those examples, or look at the problem set, practice more of them, or look at your homework or those examples for the math portions. For magnetism, 21.1 and 21.2, we can lump them together here. Give me some quick facts. Run off quick facts about magnetism. What do you know? What do you know? Stuff you know from even 6th grade, stuff you definitely know. Yeah. They're polar, good. So I've got a north and a south pole. What else? What else, Martha? Opposites attract and likes repel. What else?
The North Pole is actually like the South Pole.
On the Earth, the geographic North Pole is actually considered to be the South Pole magnetically. And down here, it's the North Pole magnetically. Okay, so the North Pole up top is really south magnetic, tilted a little bit. That's why when I use a compass, the north point on the compass points me to the North Pole, because that's actually magnetically south, and opposites attract. So the north part of the compass gets pulled toward the south magnetic pole, and that's really the North Pole named as, directly north.
Magnets create fields.
Magnets create fields. Those fields exit the North Pole and re-enter the South Pole. Those fields continue through the magnet, like this. That's what the field looks like on the right side. On the left side, it's the opposite. But we know from that experiment we did with that little clear jar and the ferromagnetic material that these lines are drawn three-dimensionally. They're out the entire thing. They're out every region. So if I'm drawing this, this also comes out this side. It also comes out of the page. Imagine this, please. Ready? Field line. You gotta see it. You can't see it on the board. Look up here. It comes like this, out of the page, and then back in. It also comes into the page, back around, and back to the South Pole. So a magnet technically comes out on this side also. It's three-dimensional. So the field lines come out in every direction from that magnet. And that's what you saw in that little fluid. You saw the ferromagnetic material on the outside of the entire thing. So magnetism is a three-dimensional force. It comes out of the North Pole and back into the South Pole like spirals, like a whisk when you bake. You know what a whisk is when you want to make eggs, scrambled eggs in the morning? Think about a whisk. Doesn't it look like this? And those spirals all come out like this? That's what I think about for this. In the magnetic field, you think about a whisk and when it comes out. What else? What else? Magnetism. Yeah. Good. A magnet is really just an infinite amount of little magnets. So if I cut this in half, and this was north and this was south, now I've got a new south pole there and a new north pole here, and now it's really just two magnets. Now, this is very useful for also magnetic domain theory. I've got a piece of ferromagnetic material. It's not a magnet, it's just ferromagnetic. It has some sort of magnetic particles in it, most likely iron, but it could be other things. That material, when it's not magnetic, the poles of all the particles are oriented in any arbitrary way. This is the way it looks. All these poles are pointing anywhere. But as soon as you induce a magnetic field around it, and we'll talk about that in a minute with a solenoid, for example, you run a solenoid around that magnetic material, now all of those arrows that you see that are pointing in arbitrary locations, they all point the same way. They're all going to point in the same direction. And that's going to be pointing in the direction of the North Pole for this now magnet. And that would be then the South Pole. So when you put a magnetic field around a material that can become a magnet, a permanent magnet, you're inducing a field on it. If it takes a lot of time to make it a magnet, it's a hard magnetic material. But that means that once you remove it from the field, it will remain a magnet for a long time. Or it'll be very strong, it won't lose its magnetism easily. Okay, another magnet can distort its field, but if it's very strong, it will not get distorted. If it's very weak material of magnetism, it'll become a magnet very easily, but once you remove it, it won't hold that charge very long, or it won't hold that magnetism very long. With the what? So the current, let's talk about that. That's a good question. In this case, the current would be traveling this way. Let me think. Hold on. Yeah. This is the direction of the current. In that end and out the bottom. In the top and out the bottom. Let me point and show you, okay? So remember, right hand rule. Take your thumb. Everybody do this. Put in the direction of the current, please. Take your fingers. Which way would they point? And if I curled them, they would go like this, kind of like curling around, like this. You see what I'm saying? A little curly? That means, just real quick, that the magnetic field comes out this end and back into this end, which is what makes this the North Pole. Okay? So if you follow this the whole way through, it'll still keep coming out the top every time. With my fingers, they're always pointing out the top. Over the weekend, practice your math. Okay, look at the problem set questions, obviously. Look at the classes review. Fast forward to see the math part. Okay?